How's everyone feeling?
Awesome, sir.
Wonderful. So question, now that we know how to calculate the direction of the induced current, how about calculating the magnitude of the induced current? Well, it turns out that the magnitude of the induced current depends on the resistance. And ultimately, to get the current in the wire, you're going to use V equals IR. But in order to calculate the current, the resistance here has to be given. But what we're going to be able to calculate is the induced voltage right here. And sometimes the induced voltage is called the EMF, or sometimes it has the script epsilon symbol there. So our mission is to come up with a formula for calculating the induced EMF so that we can rush back and use Ohm's law to figure out how much current would be produced. So ultimately, we want a formula, the EMF equals blah, 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 blah. And here's our setup. We have a current carrying, no current because there's no battery. We just have a wire in between the bar magnets, and we're going to physically move the wire downward like this. Now, does anybody want to hypothesize what one factor might be that would affect the voltage that's produced? James?
How fast you move the wire down?
Exactly. This downward velocity right here is huge. If you move it fast, you're going to get a high voltage. If you move it really slow, a low voltage. So the velocity at which the wire is physically moved downward, that is a huge factor in how much voltage is generated. Sam? Absolutely. The strength of the magnetic field. The bar magnets that you use have a huge effect. If the bar magnets have stronger magnetism and there's a greater magnetic field strength between them, you're going to get a bigger induced voltage. And there's one more variable that affects the length of the wire that's slicing through the magnetic field. Now, this whole shebang wire, this whole long wire right here, it's not all going to be between the bar magnets. So only the length of the wire that's between the bar magnets, this length right here, from like right here to right here, the length of the wire that's slicing through the field, this length right here. Now, interesting enough, if you multiply meters per second by meters by Teslas, you end up getting volts. And we're going to take a closer look at this in 1 second. Now, there is a sine theta term, but rarely do you need to use the sine theta term. So I'm going to temporarily write it in here, but I'm also going to quickly take it away. Theta has to do with the angle between the direction that you're physically moving the wire and the direction of the magnetic field lines. The bottom line is, guys, you need to know if the wire is slicing through these red magnetic field lines, you're generating maximum current. If the wire is slithering back and forth, like in a direction like this, it wouldn't be slicing through any field lines at all. So if my pen right now was the wire, I could slither it back and forth here without actually generating any electricity at all. Theta in this case would be 0, and sine of 0 is 0 and no induced current. But if I physically move this wire up and down like this, I'm going to be slicing through these field lines here. And when you slice through the field lines, or bust the flux as it's known, that's when you get the greatest current produced. So like again, just remember there is a sine theta term, but 99% of the time, you're going to be physically moving that wire in such a way that you're slicing right perpendicularly through the field lines. So this here is the formula for calculating the induced EMF. But Michael Faraday ingeniously figured out a second way of calculating the induced EMF. And let's take a look at what he did. I think I'm just going to redraw it. This time I'm going to start with the wire up above. And I'm still going to physically move it down. At a velocity v. And the length of the wire in between the bar magnets is still going to be L. And this straight down distance from here to here, I'm going to call it X. So, see if you can follow me on this, people. Watch this. We know the induced EMF, the voltage produced, depends on how fast you move that wire times the length of the wire times the strength of the magnetic field. But that velocity, I could rewrite it. That velocity, how fast I push that sucker down right here, that downward velocity, it's going to be distance over time. So it's going to be this distance x divided by time. So it's x divided by t times L times B. So this EMF is equal to x times L times B all over T. Algebraically, that's the same. But I want to take a close look at this x times L. That x times L right there, it's an area right here. It's this area right here. The length of the bar or the rod or the wire that's busting the flux. And then this distance right here, this distance x, L times x gives you this area right here. It's the area that the magnetic field lines are in. So this could be rewritten as the area where the field lines are times the magnetic field strength over the time. Yes? So this A right here is the area where the field lines are. But recall, magnetic field strength is also called the flux density. And another way of describing the flux density is you could take the number of flux lines and divide it by the area. So if you rearrange this for the amount of flux lines, the number of flux lines in Webers is equal to B times A right here. So B times A, that's exactly what we have right here. So this area times the strength of the magnetic field, what that actually is, it's the number of these red field lines here. It's the number of these flux lines right here. So Michael Faraday figured out, hey, you want to calculate the induced EMF? It's going to be the rate at which the flux lines are busted. If you're finding the average EMF, it's delta V over delta T. If you're finding the instantaneous EMF, it's going to be d flux dt. So we know that Webers divided by seconds must equal volts. And this here, this second way of calculating the EMF is known as, Faraday's law. The rate at which you bust the flux is directly equal to the EMF produced. No proportionality constants or anything. So here's one way of calculating the induced EMF, and here is the other way. And you're going to use one of these two formulas to calculate the induced EMF. And then last but not least, don't forget, once you know the induced EMF, that's what's going to go in here for the voltage. And knowing what the resistance of the circuit is, that's going to allow you to calculate the induced current.